we are going to start very soon. It's already, in fact, 3 o'clock. Maybe I tell for 1 or 2 persons who are here for the first time, I tell about today's speaker, today's lecturers. So not lecturers, but chairperson. So these are Professor Helena Zapolsky and Dr. Oksana Dobush. Helena Zapolsky is a professor of theoretical physics in University of Rouen, Normandy in France. And as we were discussing right now, she was also the participant of our lectures. She was a lecturer some time ago at the Ising lectures, and her main research interests are theory of theoretical understanding of emergence of patterns and of kinetics of phase transformations in different types of materials. And also for us, it is also very nice and very dear that she started her career, she did her PhD in Kyiv in Bogolyubov Institute for Theoretical Physics. And Oksana Dobush, she is from our institute, from the Institute for Condensed Matter Physics. She did her PhD with Professor Kozlovsky in our institute, and she is working in the field of criticality of fluids. In particular, she is interested in exact results, in understanding what is going on in supercritical region, in Widom line. So with all that said, I invite our chairperson to continue.
So maybe we will start our today meeting, and I think according to the paper Bertrand and Ralph, it's a good number of people. It's perfect, around 30. Yeah, it's an ideal number to be very efficient. And today we have a very nice and very interesting 2 presentations, and I think Oksana will introduce the first speaker.
Yes, it's my pleasure to introduce Lukas Böttcher. He is an assistant professor for computational social science at the Frankfurt School of Finance and Management, which is in Germany. And he received his PhD in applied mathematics and computational physics from Swiss Federal Institute of Technology in Zurich in like 5 years ago, yes. Mm-hmm. So his research embraces advanced computational and analytical methods to tackle real-world problems in the social sciences, medicine, and biology. And among his research topics are also fundamental questions in applied and computational mathematics, statistical mechanics, and machine learning. And he also works on applied research as epidemic processes and political polarization and the rapid rise of antibiotic resistance. And today we're going to listen to his lecture named Applications of Artificial Neural Networks in Statistical Mechanics and Nonlinear Dynamics. So please, Lukas.
Okay, yeah, thanks a lot for the introduction. So I hope that you can all see my screen.
Yes. Yes, it's full screen mode. Thank you.
Okay, perfect.
Great.
Yeah, thanks again for the invitation. It's a great honor to be part of this great lecture series, the Ising lectures, and I'm not only honored but also surprised that you're doing these lectures for like already 24 years. That's that also shows that there's a lot of interest in these topics. And I was thinking about maybe talking about epidemic processes because of the, connection to the COVID-19 pandemic. But then I realized that you already had another speaker talking about them, like epidemic processes and disease dynamics. So we focusing a bit on artificial neural nets, and that's more tutorial today, and I will also discuss some of our research in first of all generative neural networks and connections to statistical mechanics, and also applications of certain types of neural networks in nonlinear dynamics. And I think that last part can be very interesting also for some of your students or junior faculty members who want to start with something really new. That's a brand new topic. Like some of these ideas are maybe 1 or 2 years old, and people are now trying to understand all these features associated with these types of neural representations of ordinary and partial differential equations. And right, so just to give you a brief idea of the outline of my presentation, I will start with a relatively brief and also broader introduction of feed-forward neural networks. And in the second part, I thought that it would be nice to somehow connect this presentation to Ernst Ising's work. And so I will talk about learning the Ising model with generative neural networks. And on the right-hand side of the slide, you can see different Ising configurations that have been generated with standard metropolis or MRT squared Monte Carlo schemes, but also with restricted Boltzmann machines and variational autoencoders. And this work, there were a few other papers on that topic, but this work in the past few years also triggered a few follow-up studies, I guess. So there are now many groups who are that are exploring different types of neural networks and their applications on the Ising model and other types of models in statistical mechanics. And in the last part of my presentation, I will talk about neural network-based control, this applications of neural networks to controlling dynamical systems. And then I will briefly summarize some of the main findings and also talk about like possible future research and maybe some possibilities for, say, junior researchers, doctoral, postdoctoral students to maybe work on these topics in the future. Right. So I started with a brief introduction to feed-forward neural nets. But one of the simplest ways of starting with this topic is to just consider a few standard Boolean functions. So we could basically think of a neural network as a composition of different neurons that are connected via different types of connections. And now, like this neuron C here on top of the other neuron A can get activated if both inputs, like it has two inputs, and it can be activated if both inputs are one. So it needs two inputs. That's just a definition that we use in this figure. And we can basically represent an identity operation using this kind of diagram, or like this kind of simple neural network. It's a very shallow neural network that just consists of one processing neuron and one input neuron, and we can also map other types of standard mathematical operations on binary objects, for example, an AND operation, on OR operation, or also an operation that involves some negation operators. And that's just to say that we can represent certain standard mathematical operations with like these simple types of neural networks that just consist of one processing neuron. And that's basically what's called, in a like more general formulation, what's called a perceptron. And the perceptron has been developed by Frank Rosenblatt. And it's basically just, again, like a single neuron that processes different types of inputs. And all these inputs are being multiplied by corresponding weights. And then we end up with a weighted sum. So we have a weighted sum C that is equal to the scalar product of our input vector X and our weight vector W. And then we feed it into some activation function, which could be a simple step function, but it could be also like another type of function, maybe something smoother. We will see later on that sometimes it's better to use smoother functions if you want to work with these types of function approximators, right? So and you also see on the right that, of course, what we are doing today on digital computers, and which may take a few lines of code, took a lot of hands-on work in the past. So Frank Rosenblatt was implementing some of these ideas on analog computers, and maybe some of you might be interested in like connections between analog and digital computing, because I'm not sure, but maybe some of you have seen that many companies are now trying to basically redevelop or implement some of these analog computing ideas on special purpose chips, because it's for certain applications just more efficient to really implement these structures as they are in using analog circuits instead of digital circuits. So what Frank Rosenblatt did on this picture seems a bit outdated, but in fact, what we are seeing right now, what many companies are doing, is exactly what he started with, but of course a bit more compressed and like downscaled, so that we can use it on smaller chips, right? And so for Frank Rosenblatt contributed to all these early developments on particularly artificial neural networks and machine intelligence, but he died very early at the age of 43, basically on his 43rd birthday, because of a, I think, sailboat accident. So yeah, he had a relatively short life, but still made all these great contributions to learning theory. And what's also interesting about the perceptron is that its learning rule, which is connected to Hebbian learning, is a bit different from like the standard techniques that we use in other types of say feed-forward structures, which is basically called backpropagation nowadays. And Hebbian learning can be implemented as follows. So we have these weights associated with certain inputs, right? And we update weights by using a previous weight entry or a previous weight vector, and then we add the difference between the desired output value of perceptron for a given input and the actual output that we achieve with the current perceptron, and then we multiply it by the corresponding input vector and by the learning rate. And this learning rule is also called Hebbian learning, because you see that there's a proportionality to the input vector, to the difference between actual output and the current output of the perceptron. And that basically means, in a slightly different interpretation, that neurons that, like that's the standard sentence, that neurons that fire together, wire together. So you connect neurons that fire together. And now I also wanted to show you like an application or an example. So I prepared a code repository, and you can also use it later on if you want. It's called, I think it's called Ising lectures. And I will show you the link later on again, because I think we can send it around right now in Teams. But I have this repository, gitlab.com, computational science, Ising --lectures-2022. And I have a few examples for you. I can also try to zoom in a bit. And this example is a simple perceptron, and whose goal is to basically identify certain samples and their corresponding classes. So we want to learn if a certain sample belongs to class 1 or class 2. Class 1 could be fluid disks, and class 2 could be red triangles. And now we are interested in basically learning a linear function, right? So everything that we need to learn is a like linear separator between these two regions, and that can be implemented in terms of a perceptron. And here I'm implementing two perceptrons in Torch, and one perceptron uses the assign function as a activation, and the other neural network or the other perceptron uses an identity activation function. So it basically has no activation. And you can also later on maybe just go through this example. I will now show you that one can implement a perceptron and train it and basically learn weights that lead to this linear separation between data points. And in the first example, I'm using an identity activation, and you see that it takes about 2,000, let's say about 2,000 epochs to converge to certain weight values that are really able to separate these data points well. And we also see it here, like if we plot the loss, and by loss, I'm basically plotting the difference between predicted Y values or output values and actual output values or desired output values that we want to achieve. Like for these data points, it would be, so we want outputs that are -1, -1, or 1. And here I'm basically calculating differences with respect to these outputs and the generated outputs of the perceptron. And we also see here that it takes about 2,000 epochs to converge. And that's the second experiment. Now, if we replace the identity operation by a sign function, we can basically achieve convergence after about 9 epochs of training. So that shows that, of course, activation functions and picking specific activation functions can be quite useful in terms of predicting predicting certain output values. And if we know that we are dealing with binary outputs, it's of course recommended to use some kind of activation that has that only produces 2 different values instead of having something like an identity activation. Okay. And that's of course like relatively old-fashioned, but still the perceptron was one of the starting points that led to further developments in machine learning. Also because Minsky and Papert showed in their book Perceptrons from 1969 that they cannot represent XOR functions. And there is still some debates about if they did that on purpose, and if they've probably known that one can just add a few additional layers and basically still learn XOR functions, or if they weren't aware of that. And if you're interested in further information, I can highly recommend the Wikipedia article on perceptrons, the book by Minsky and Papert. And they also discuss the so-called XOR affair that led to the first, or to the so-called AI winter, where funding agencies stopped investing into like neural network related research because people thought that one can't use them to learn simple functions such as XOR. But in fact, it's of course possible to learn basically arbitrary functions if one uses sufficiently complex neural network architectures. And that's what's usually being called a multilayer perceptron or an MLP. So an MLPs are, depending on the activation functions that one uses, it can be shown that they are universal function approximators. And there's some older papers from the 80s and 90s that already established universal approximation characteristics for certain types of activation functions and certain types of neural networks. But also in recent years, there are more and more papers coming out also from the statistical mechanics community that look at like capacity and bounds associated with neural network width and like basically numbers of neurons per layer and number of layers, right? So they're looking for these two characteristics and try to connect it to certain activation functions to find out if certain types of neural networks are able to represent certain types of functions. And now, like, if you think about it, we have talked about perceptrons and Hebbian learning, like a very simple learning rule that can be used to train these simple perceptron structures. But what about MLPs? Like, it's a bit more complicated to train these relatively large neural networks, and it also took a while to come up with a efficient algorithm, which is nowadays being called backpropagation and implemented in almost all standard machine learning libraries. And one of the papers that is often cited in the context of backpropagation is Rumelhart, Hinton, and Williams' work on learning representations by backpropagating errors. But also here, if you're interested in some additional information, you can, for example, Google backpropagation and history. And there's some earlier works on that topic, also by I think, Finnish computer scientist or mathematician, Linnanmaa, who used some of these ideas in a slightly different context, but which are basically quite related. And there are still many discussions about who basically came up with these ideas of accumulating gradients in a composite function. Yeah. And I also want to briefly talk about backpropagation because it's a really useful algorithm. Also, if you're interested in studying large-scale composite functions, and I think also for, again, like there are many research efforts in statistical mechanics to try to tackle some of these learning questions that or standard problems or standard questions in learning theory that I will briefly talk about in 5 minutes or so. And in order to understand some of these questions and some of these problems, it's also useful to maybe focus a bit on some of these standard techniques that one uses for training multi-layer perceptrons. So in backpropagation, we are again considering an MLP. We have an input layer, certain number of hidden layers. There are also potentially different numbers of neurons per hidden layer, and there's an output layer, and we also have a loss function. And this loss function depends on the losses associated with different types of samples. So we could have a data set, and for example, with different features could correspond to maybe temperature, humidity, weekday, and time, and we are interested in predicting the number of people on campus, for example. So that could be an output variable, and each I would correspond to a different measurement. So we have n measurements, and we are basically interested in minimizing, say, the prediction error, the difference between the predicted number of students on campus and the observed number of students on campus. And again, because we are having universal approximation characteristics for sufficiently deep neural networks, certain types of activations, we can assume that we are in principle able to represent such a relatively general prediction function. And now our goal is to adjust the weights, so they're different weights connecting all these individual neurons. And now we want to adjust these weights using certain types of steepest descent updates. One can also use more sophisticated updates, but just for the sake of simplicity in this presentation, I will focus on steepest descent. So we are trying to calculate the gradient of f with respect to all of these weights, and then update all of these weights using these standard gradient updates. Now, let's say each neuron or each like output of a certain neuron depends on the weight of the previous layer multiplied by the output of the previous layer plus potential bias terms. And sigma is usually used to denote an activation function, which could be a simple linear function, a step function, something like a max function. And we will also use set to denote this argument, v times x plus b. And that's also standard notation in learning theory. And we can consider as an example a loss function, something like a mean squared error, where we take differences between the neural network output and the desired output. And now the question is, how can we efficiently calculate these gradients? So how can we calculate nabla f with respect to omega? And the idea is that we basically accumulate certain quantities or calculate certain quantities in the forward path. So we send information through the neural network in the forward path, and then calculate gradients in a like in an efficient way in the backward path. And the standard approaches, and there are multiple types of backpropagation algorithms and more sophisticated approaches, but the standard way of doing that is to calculate these quantities delta Lj, which is the partial derivative of the loss function with respect to a set, with respect to these activation function arguments. And if you do the calculation, so you basically just need to replace one of the arguments in the activation function by the input of the previous layer, you can basically rewrite these deltas in terms of the sum over deltas in the next layer multiplied by corresponding weights and the derivative of the activation function. Now, these activation functions are typically known and differentiable. And so this is something that we don't need to calculate numerically. So we can often evaluate these derivatives analytically. And that's also what makes training, at least of some of these architectures, very efficient, because we can directly calculate these derivatives. And we can also evaluate derivatives of f with respect to bias terms and with respect to weights. And we see that there's always a connection between these derivatives and derivatives in the next layer, or the derivatives in the same layer. So what we basically need to do is we need to calculate some of these quantities set and x in the forward path. We know what our weights are, and then we need, in a smart way, we somehow need to evaluate gradients in the backward path by efficiently accessing and storing variables that we accumulated in the forward path. So we don't need to store all of them. just need to, so we don't need to store all of them the whole time. And that's what I wanted to say. We just need to store some of these quantities as long as we need them to calculate these some of these recursion relations that I showed on the previous slide. And usually one also combines these types of methods with stochastic gradient descent. That means we just use a certain subset of samples and not all samples to make training more efficient. And that's what I wanted to show you as a starting point, because I think that's something where statistical mechanics, or also researchers who are active in applied mathematics, can still contribute a lot, because there are so many open questions that appear to be very simple, and so many ongoing discussions without any meaningful conclusion, in my opinion, that yeah, there's still space for a lot of very fundamental research in this field. And some of these open and debated questions are, why do over-parameterized structures on neural networks generalize very well? So in many cases, for example, last week I ran some simulations on a like image classifier. So I didn't train it, but I wanted to understand some of these structural properties. And that classifier had about 6 million parameters. So it's a very high dimensional function, and you can basically try to understand some of the underlying functional properties. But one also sees that you basically have many more parameters in many of these applications than input features. And one core question is, why do these structures generalize very well to other types of related data sets, maybe not to completely different tasks, but other types of maybe image classification tasks? And a related question is, how can we predict generalization properties? So that's also not very well understood, because if you look at the literature, there are different attempts to connect properties of found minima to generalization error, but it's very hard to come up with a general technique or like definition of what generalization error, not like what generalization error means, but how to quantify or predict how certain properties of a, let's say, trained a neural network or trained function translate into generalization properties. So that's also a very interesting question. Another interesting question is, what number of parameters is most effective given a certain data set or application? Or why does or doesn't SGD approach bad local minima? And that's a discussion that I had recently with a colleague who started writing an introduction for a paper where we want to explore some of these generalization properties, and he started writing about the basically good properties of SGD and its ability to converge towards good local optima. But there are, in fact, also many papers that say the exact opposite. For example, this one, a bad global minima exists and SGD can reach them. And again, like if you start reading some of these papers that are typically very short, very compressed, it's close to PRL letter style, and often also not very theoretical, you will see that, yeah, there's, I think, a lot of work that can be done from a statistical mechanics perspective. And also, when should training be stopped? That's also a bit related to generalization properties, or like what type of minimum did we reach? Is it already a good minimum, or should we train further? And this paper by Cooper, which was published in the Siam Journal of Mathematics of Data Science, is very interesting with respect to like this question, because it mathematically characterizes global minima of over-parameterized neural networks. So Cooper derived some properties using very general assumptions of what global minima of standard neural network type functions look like and what properties they have. And I can highly recommend this paper. It's also interesting to see. So because nowadays many of these reviews are like conference reviews are published online on openreview.net, and this paper is kind of interesting because I think it's a amazing contribution to the field. But Cooper first submitted it to the International Conference on Machine Learning, and you can find all the reviews online. And they basically said that it's not useful because it's something that is kind of known or something that seems relatively intuitive, and one basically like this paper basically lacks some of the standard ideas in the ML community that one should focus a bit more on how to improve certain things to maybe achieve a slightly higher training accuracy or something like that. But on the other hand, people in the community are also complaining that there's a lack of solid theoretical contributions that focus on, let's say, the like characterization of global minima or properties of loss functions. And I think that work did a really great job in proving some of the standard characteristics of these functions, and then it ended up in a more mathematical journal. But yeah, I like the contribution a lot. Yeah, and here's some visualization. So there's also always a question on like how can we even think of 1 million or like functions with 1 million or 10 million parameters? Can we somehow project them? In some papers use random projections, other papers use different kind of projections. And also here, there's some nice work that could be done on the intersection of like differential geometry, information theory, and learning theory. And also in this part of the literature, I think there's still a lot of space for nice contributions from the physics and applied math community. Okay. Right. So now I want to move on with the more Ising lecture-related topic, the Ising model, and how to learn it with generative neural nets. And I want to start with a brief introduction to Hopfield networks, because that's the basically starting point for the development of Boltzmann machines and restricted Boltzmann machines. And let's say we have like some types of McCulloch-Pitts neurons, which are again like kind of similar to the perceptron structure. We have inputs x1 to xn, weights, a bias term, an output, and an activation. And the activation is given by all the weights multiplied by corresponding inputs. And we also shouldn't forget to add the bias term, and then we have a certain activation. And the main difference with respect to previous slides on MLPs and perceptrons is that the Hopfield nets only work with binary states. So states can be either 1 or -1, sometimes also 1 and 0. And the activation determines if we switch or if the state will stay active or if the state will become inactive. And you see that Hopfield nets are interesting also because they have this kind of time evolution. So Hopfield nets themselves are some kind of like neural network with an internal dynamics that that depends on the initial state initial weights, etc., initial biases and inputs, and the values of the activation function, and then we can observe like different kinds of switching patterns in these types of networks. And there's also an energy that can be associated with Hopfield nets. And now, like what you're seeing here is that these types of Hopfield nets are basically deterministic because we can always calculate an activation function value, and probabilities involved depending on the activation function value. We switch a certain state to either a 1 or -1. But yeah, like that's basically it. And the problem with these structures is also that one can store certain patterns in them, and you may also see connections to spin systems, right? So we can, like, we have this type of energy functional, and we have some kinds of state switching dynamics, and we can store certain patterns in local minima by adjusting these weight values in accordance with the input data that we want to learn. So that's the basic idea with Hopfield nets, storing certain patterns in local minima of basically spin systems. Yeah, and there's an interesting video if you wanna hear some comments by John Hopfield himself on Hopfield nets and physics of the mind and neurobiology. I can highly recommend this podcast by Lex Friedman. But yeah, like as I said, one of the problems with Hopfield nets is that yeah, they're deterministic. They can get stuck in certain bad local optima. They have a relatively limited capacity, so they can only store a relatively limited number of data, of information, and one possibility to generalize some of these ideas related to Hopfield nets is what's called a Boltzmann machine, or particular restricted Boltzmann machines that can be trained more efficiently because they only consist of these two separated layers that have no intra layer connections. So we have a visible layer and a hidden layer, and visible units are connected only to hidden units. Visible units and hidden units are not connected to each other among themselves. And that's also what makes training more efficient. One could also think of standard Boltzmann machines, but there all the individual neurons are completely connected, and that's a bit harder. Yeah, these structures are a bit harder to train. And for restricted Boltzmann machines, or RBMs, we also have like instead of deterministic updates, we have probabilistic updates, which are similar to Klauber updates in statistical mechanics. And the basic idea is that we have this kind of activation probability that depends on the energy difference associated with a certain neuron, or like switching the state of a certain neuron. And there, in principle, one could also define some kind of temperature to tune the activation function a bit more. And how do we update weights in restricted Boltzmann machines? So usually one uses some connection between. So the goal is basically to learn a certain distribution that is connected to the visible unit. So we want to learn a certain input distribution, and then we want to generate new samples that are distributed according to that input distribution. So these are generative neural networks. It's a bit different from classifiers, right? And RBMs are generative structures, and in order to update weights, we first connect our input distribution to the visible units. So we need as many visible units as there are like features associated with our input distribution. For example, in the top left corner, I'm showing you a 5 that is being generated by an RBM. And that's, I think, a 32 by 32 or 28 by 28 image. And so we need either 28 by 28 or 32 by 32 visible units. And in this example, I don't remember the exact number anymore. And that's basically what defines the first average in the weight updates. So data means that we connect data to our visible units, and then we are doing these kinds of Glauber updates on the RBM. So we change states, and we're calculating these ensemble averages between visible units and hidden units, and then we subtract the model generated ensemble average. So we disconnect the data from the visible units and again calculate the ensemble average. And that's usually relatively challenging to do in terms of computational power, because in each training step we would need to sample many configurations, and that's computationally just not feasible in many applications. And that's why one often uses what's called contrasted divergence, where one just uses k steps in the model update and zero sampling steps in the data update. And then one can still try to use averages over like a certain number of batches, but there are not that many updates that are being used in these types of averages. So that's that's the contrasted divergence part. And again, like the top left corner, you can see a number that is being generated by such an RBM, and we also applied it to Ising configurations that we generated with standard MRT squared algorithms. And so I think we generated about like a few thousand or like up to 20,000. I don't remember the exact number anymore, but a few thousand standard Monte Carlo samples of Ising configurations at different temperatures. And then we used one RBM. Like in this example here, we used one RBM to learn the distribution of magnetization, the distribution of energy, and the correlation functions, just based on input images. So instead of using numbers, we used input images 32 times 32 that we generated with standard Monte Carlo sampling. And we can see that RBMs can capture mean magnetization, say at the high temperature phase. So we have about zero magnetization, and we can also capture the variation of magnetization in these samples. And we were also able to learn the energy of these samples, and also correlation characteristics. Now, what's interesting is that depending on the types of RBMs we use, or the types of training approaches we use, we got slightly different results. And we also compared it with another generative neural network. So here we were studying the magnetization as a function of temperature. And we see that there's a good overlap, or like a good correspondence, between RBM generated samples and MRT squared generated samples. And we also see that basically energy and correlation functions are also are also being captured relatively well by the RBM. So one could, in principle, use these types of neural networks as sample generators, but I still doubt that it's more efficient than just using MRT squared or standard Monte Carlo sampling. So I don't think that it's more efficient, but one could in principle use them to generate Ising samples. Like our idea was a bit different from just using these machines to generate samples. We basically wanted to study or compare restricted Boltzmann machines and other generative neural networks in terms of their learning capacity by using like an exactly solvable physical system, because usually in the machine learning community, they only use a very small number of standard data sets like MNIST, these numbers, for example. And then many of the claims that are being made are simply based on a few data sets. And that's why we wanted to consider a data set like related to an exactly solvable physical model that we can study and where we can also measure and quantify some deviations with respect to quantities that we already know or know how to simulate or calculate them exactly. And that's what we did. And that was also kind of surprising because we compared the ability of restricted Boltzmann machines to generate samples at different temperatures with the ability of other generative neural networks, so-called variational autoencoders, to generate such samples. And variational autoencoders are usually being called superior to RBMs with respect to their like learning characteristics and representational capacity. But what we have seen is, and you can also see it here in this, these two plots, is that RBMs are able to generate samples at different temperatures that are, you know, like more or less uniformly distributed. So we have slightly more samples at the critical temperature, but they're still, like they're still able to generate samples for different temperatures. But for the variational autoencoder, we found that it was really hard to generate certain types of samples, for example, close to the critical temperature. And we also identified some issues in terms of how to train some of these networks. For example, in the RBM, we could use single RBMs to learn a single, like the distribution of physical features at a single temperature, but we could also train one RBM with all samples at all different temperatures, and it still worked out relatively well. But for the variational autoencoder, like the single temperature training didn't work that well at all. We somehow assumed or guessed that for the autoencoder, it was helpful to have additional samples from configurations that are easier to learn. Let's say where many spins are 0 or many spins are 1. So we thought that may help autoencoders to learn certain distributions. And that's a short summary. So training RBMs can be challenging and computationally expensive. And traditional RBMs only handle binary data. The problem is that, for example, variational autoencoders have difficulties to generate Ising samples at the critical point. And RBMs achieve similar or better performance than variational autoencoders without convolutional layers, which are, so convolutional layers are usually being used to learn image information. And we have seen that RBMs don't really meet that in this specific application. And I already mentioned the training on all samples or just like samples associated with one specific temperature. So yeah, that's basically it on the like learning statistical mechanics models part. And now in the last part, I want to briefly talk about dynamical systems and neural ODEs. That's also a very interesting topic, relatively new. There were a few research efforts also maybe about 5 years ago already, where a collaborator of mine told me that people didn't call it neural ODEs back then, but they called it something like a Runge-Kutta nets. But because I guess that some people didn't know what Runge-Kutta methods are, it didn't trigger that much interest. But neural ODEs sounds a bit more related to ODEs and ODE solvers, and that basically triggered a whole wave on new ideas on combining neural networks with dynamical systems theory and learning and controlling dynamical systems. And for those of you who are interested in maybe reading a bit more about these types of neural networks, I can highly recommend PDF or doctoral thesis PDF on neural differential equations by Patrick Kitcher. See, it's like 230 pages, very comprehensive overview of state-of-the-art research on neural ODEs, and I want to connect it a bit to controlling dynamical systems. So we worked more on the control part in the past 2 to 3 years, and controlling dynamical systems, like in the literature, if you check some papers, is mostly connected to like lunar landers, which basically means that we want to land a spaceship, a lunar spaceship on the moon, but in a very specific area, using maybe also minimum fuel. So that's a standard application that people often use also in papers to show that their methods work. Then there is the real world counterpart, SpaceX, where I don't think that they use neural ODEs, but they probably also use some sophisticated control engineering techniques. And another standard example that you often find in papers is the standard cart pole system, where the goal is to stabilize a pole on the cart, and by just moving it around on the x-axis. And there are, of course, also other applications, more applied, like applied topics that are related to controlling certain dynamical systems, for example, Wobbard arms. And these videos are taken from the Bear group at UC Berkeley, and they also, like in this project, they didn't use neural ODEs, but they used reinforcement learning techniques. And now in traditional control theory, a dynamical system is said to be controllable if it can be steered from any initial state to any target state in finite time t. And in optimal control, the goal is usually to minimize a certain functional that consists of an integrated cost and a final cost. And this functional is subject to the constraint x dot equals f of x comma u. And this constraint is basically a dynamical system that depends on the system state, but also on the control function u. And now we want to steer something from x naught to x star in finite time. And maybe like one standard control goal is to use a minimum of energy, or to have a relatively small norm of the control signal u. So that's one standard control goal in optimal control. So we would replace L by the squared norm of u, for example, if we are interested in standard optimal control. Right. Now, traditional control theory relies a lot on Pontryagin maximum principle, and also on the Hamilton-Jacobi-Bellman equation. But the problem is that usually, if you want to solve certain real-world or like complex control problems, it's very difficult to directly apply Pontryagin maximum principle or to solve the Hamilton-Jacobi-Bellman equation. And then there are many approximations, many direct and indirect numerical methods that one can use to solve these types of optimal control problems. But even these methods are sometimes numerically very unstable or challenging to solve. And there's still a lot of interest in controlling high dimensional and also potentially stochastic dynamical systems. And that's something that so I have another notebook that I will show you and share with you later on. And we were working on like combining neural ODEs with control theory to develop something which we call a neural ODE controller, or also the like AI Pontryagin framework, because it's a bit related to the maximum principle approach, as we will see in a few seconds. And the basic idea is that we have a dynamical system on a graph G, and it can be a relatively large dynamical system, and we know it's dynamic, so we know the underlying evolution equation of system states, and then we can in principle solve these evolution equations with a numerical ODE solver if we don't know how to calculate solutions analytically. And then we also observe certain types of uncontrolled ODE dynamics. So we don't reach any target state, we're just solving an uncontrolled ODE system, and now we are interested in controlling certain parts of the system to steer the dynamics towards a certain target state. And that's what we're doing here. So we are basically connecting a neural network to certain nodes in the underlying graph, so-called driver nodes. And as we have seen in previous slides, neural networks, if corresponding universal approximation theorems apply, are in principle able to approximate arbitrary functions. And control engineers also use these techniques in certain applications, because neural networks are basically just like in this application here, just another type of basis functions, so to say. So instead of using polynomials or for example, like spectral methods or things like that, to learn or parameterize control functions, we can also use neural networks. Now, the interesting feature of neural ODEs is that they're extremely simple to train. And we also found that it's very stable. It's numerically very stable. And I will show you an example in 2 seconds. And yeah, so basically we are connecting a neural network to driver nodes. We are letting the system evolve. And at the end, we will realize that the system may not reach the desired target state, but then we calculate the difference of reached state and target state and backpropagate gradients with like standard backpropagation, as I've shown you in the like in the previous slides. And yeah, and that's basically it. So there's no more magic going on. We're just using a neural network to parameterize control functions, using backpropagation to adjust a neural network weight, and then we can try to control dynamical systems. And that's just another illustration of how to time unfold the underlying ODE system, backpropagate gradients, adjust neural network weights, and hopefully train the neural network so that we can reach the desired target state. And now a simple application. So we use linear dynamics with this type of interaction matrix and a control matrix B that indicates that, yeah, we're just controlling one node or like one state of our system. And we're using a loss function that just calculates the difference between reach state and target state. And here you see that in this example, the optimal control indicated by the dashed black line is not going against the vector field, although it's shorter to go in this direction, right? So that would be like geometrically somehow shorter if you just calculate the distance between these 2 points, to just go against the vector field. But because we don't want to spend too much energy, control energy, it's more efficient to go with the flow of the vector field. And that's also what the neural network learns. Now, what's surprising is that we didn't specify that we don't want to go against that we don't want to go against the flow. So we didn't specify it in this loss function, but still the neural network kind of goes with the flow of the underlying vector field. And that's also because we initialized it with relatively small weights, and so the neural network can explore the underlying vector field, which is quite interesting. And you also see it here that it's basically learning optimal control without being told to do so. And that's an animation, so of the learning dynamics. The blue or solid blue line is the neural network solution, and the dashed black line is the optimal control solution. And it takes about 2,000 epochs to 2,000 to 3,000 epochs to reach the target state with a solution that is close to optimal control, right? And then sometimes one sees little spikes in the training process, because there's always a trade-off between getting very close to X star and maybe implicitly minimizing this type of control energy. Okay, and yeah, we also applied it to other systems like Kuramoto dynamics to synchronize oscillators, but not only to synchronize them, but also to, for example, generate 2 different phases on a square lattice. So you see here that first, all these oscillators are uncontrolled. Then we can use a neural network to steer them into a state where we have 2 different phases associated with 2 different oscillator phases, basically. And we can also use a neural network to synchronize oscillators, which is a bit simpler than generating these 2 different phases. And yeah, all these source codes are also available online on Git, and you don't need heavy computing machinery for that. So all these examples were run on my laptop. That's another advantage of these neural ODE type systems. It's relatively simple and straightforward to train, to use, and they're quite stable. And we also apply them to epidemic dynamics. In this example, we compared neural ODE controllers with reinforcement learning, and our goal was to protect a certain subpart of a square lattice indicated by regions G star, and we wanted to protect it with limited resources. And we had like an epidemic starting in the top right corner of the lattice. And you see that it's also kind of interesting that reinforcement learning and the neural ODE controller, they're kind of doing the same. So it's a very similar evolution characteristic in both scenarios. Okay, like to summarize neural network control, approaches are useful to control high-dimensional dynamical systems. We observed better runtime performance up to 2 orders of magnitude faster and very high numerical stability in comparison to other control methods that rely on Pontryagin's maximum principle or solutions of the Hamilton-Jacobi-Bellman equation. And on Cannon principle also apply these techniques to stochastic dynamics. And there are many interesting applications and possibilities for future work. For example, combining these neural network-based modeling and control approaches with the study of partially unknown systems, because there might be some physical systems that we know how to characterize in terms of their, say, Hamiltonian, for example. We can write down a very general Hamiltonian that should in principle be able to capture the dynamics of a certain system, but we don't really know all the parameters or all the details associated with this Hamiltonian. And then we can use some type of constraint training. So we constrain training on the underlying Hamiltonian of the systems that we wish to study. And yeah, like here are a few code repositories. I can also share my slides later on if you want. So one repository is focusing on the Ising model, and you can download all the source codes. It's very well documented, I guess. And it was done by one of my former students, Francesco. And yeah, like he did a really amazing job also in documenting all these codes. We have all neural network control codes available on this repository, and we still need to work on some tutorials because people found it a bit hard to apply some of these methods right away. And I also, again, like I added some example scripts on another repository, which I call the Ising Lectures 2022. And I think there is, yeah, like one thing that I wanted to mention, I probably can't show you the other examples anymore because we don't have enough time, but I will just show you the repository again and you can explore these examples later on. I wanted to briefly mention 2 points. First of all, we have a master's program in Frankfurt that focuses on applied data science, with courses in computational statistics, deep learning, machine learning, fundamentals, NLP, numerical analysis, and we have scholarships available for excellent students. So if you know someone who is interested in enrolling and they, even though they need scholarship support, they can contact me or our study advisory services. And I also wanted to mention that if you know that some of your colleagues are maybe unable to continue their studies at the moment because they needed to leave university or are just, you know, experiencing some trouble at their schools, they can also either enroll into some of these programs, maybe in the applied data science program, or receive some support for other types of like research assistance scholarships or something like that. So there are possibilities. I just wanted to mention that because I thought that some of your colleagues might be interested in that. And just very briefly, so in the computational science Ising lecture Git repository, I have the perceptron example and also the neural ODE example. I won't go through it, but it's basically learning a dynamical system with neural ODEs. And there is the neural ODE control example that I've shown you in the third part of my presentation. And you may remember this curve. So that's a neural ODE controller that learns to control that simple linear dynamical system. And yeah, please feel free to use it, extend it. I thought that it might be interesting for some of you. Okay, yeah, thanks a lot, and I stop here.
Thank you, Lucas. So maybe there are some questions. We have, I think, time for a few short questions. So please raise your hands or unmute yourself and ask. I see Yuri Holovach, please.
Yeah, thank you. Thank you very much for the talk, and especially also that you provide some codes to work with afterwards. The question is the following. That's about the last part of your talk. And you mentioned about analysis of Kuramoto dynamics and of spreading processes. And somehow the examples you showed were about lattices, say how synchronization occurs on lattice. I don't have a good feeling. For example, if you are interested to study the same process of on the network or on scale-free network, is it feasible by your method? Should be? Is it at all possible doing similar technique?
Right. So we I didn't show the. So we also did what Strogatz, Erdős Rainey, lattice, and scale-free. So we did that. I just didn't add it because it's always a bit harder to visualize. It works, and what was also kind of surprising is that we also studied systems that were theoretically proven to be uncontrollable, like linear systems that are basically uncontrollable by arguments from standard control theory, but like these neural networks don't care, right? Because they try to get as close as possible, which is also interesting. So in principle, one could also use some of these ideas to control systems that are very hard or not controllable.
Okay, yeah. Thank you.
Thanks.
Reinhard, please.
Yeah. I would like to ask you to the Ising model, of course. So as I understood, you need Monte Carlo calculation in order to train your network.
Right.
And then you can make predictions. So what do you gain if you make predictions instead of making another Monte Carlo calculation?
Right.
So
right.
That is the first question. And the second, if you do this and you can gain something, at least some time or so, is there a difference between universal quantities and non-universal quantities? For instance, UTC or some exponents or amplitude ratios. So how is the situation there?
Right. So yeah, no, that's also what I wanted to say, or what I briefly covered in my presentation, that in terms of efficiency, it doesn't make much sense. There are many papers that talk about using these types of structures to generate new samples. It's not more efficient. So if we have all these sophisticated Monte Carlo approaches, also like something like cluster algorithms, for example, it's not more efficient than using some of these approaches. Like we wanted to study these systems and show the ML community that one could, in principle, use other types of benchmark models to compare the learning capacity of neural networks, because they have basically maybe 4 or 5 standard data, that's MNIST and ciphers, like numbers and faces and these types of things. And to your second question, so yeah, like first question, I completely agree. In terms of generating samples, no gain, and I wouldn't use it, right? Because the quality is always worse than in the original data. So I wouldn't do that. To the second question, so we studied a few characteristics we didn't look into some of the quantities you mentioned. I know that some people are also interested in learning so they're not only interested in learning the distribution of samples, but also learning the position or exact position of critical points, for example. And also there, so I've seen and I've reviewed a few papers on that. It's not, yeah, I think it's not more efficient than other approaches that exist out there, because like existing techniques are especially like they're developed to just do one specific thing, like basically identifying critical exponents or critical points or generating new samples. So I would say that, yeah, it's not that useful, but more useful to use some of these techniques from the statistical
to learn
mechanics.
something about the neural system,
right,
and not
right.
about Ising system. So
right.
Okay, so
right.
Thank you.
Right.
Is there any questions? No. So thank you, Lucas, for such a good lecture. And I think we should finish our first session.